All right, good deal. Let me start my timer here. Thanks, Eli. I'm Zach McEachran. I'll be presenting on some of my dissertation work on the effects of the Pagami Creek fire on water yield and peak flow in the Cowish River in the boundary waters. My co-authors are Diana Carwin and Rob Slesak. Uh-oh. Oh, there we go. So I guess first I want to just to give you an overview of what I'm going to talk about today. First, I kind of want to set the stage of kind of forest hydro in general, and kind of how we know what we know, what kind of work has been done in the past in our area, and how this new study on the Cowish is kind of a unique contribution, especially in the context of the watershed management and planning we do here in the state of Minnesota. So we know that forests are really prime regulators in the water cycle. They help control water quality and habitat, with generally the number one negative effect of forest disturbance being increased sediment yield in our waterways. Forests help mitigate flood risk, and forests just help regulate how much water in a given year flows out of the watershed as stream flow. This is because forests use a lot of water as evapotranspiration. Greater than 50% of all precipitation that falls returns to the atmosphere as ET. On my study sites, that's 65% of annual precipitation at the Marcel Experimental Forest, on the Chippewa National Forest near Grand Rapids, Minnesota, and almost 80% in the upper Cowish watershed. In the past, how we've assessed, okay, how does forest disturbance, so maybe harvesting or fire or wind throw, etc., affect stream flow? Because we know then you don't have trees using water in that area anymore. Generally, we've used what's called the paired watershed approach. So you have two small watersheds. I'll try to do all my hand motions on Zoom here. You have two small watersheds right next to each other, similar in physiography, similar in cover type, etc. And you calibrate them for several years so that you can get a relationship between control and treatment. Then you cut trees on one of the watersheds and you can assess the effects with respect to that control watershed. So you can directly attribute any change in stream flow to the harvesting or land cover treatment that you do. So we base a lot of our management knowledge on these paired watershed studies. But there's kind of a little bit of a mismatch here, because as you can see on the Marcel Experimental Forest, where we've had these paired watershed studies in Minnesota, you can see our small trickle that goes into a weir pond here, versus on the right-hand side, the Mississippi River going through Grand Rapids. Where do we do watershed management? Well, generally at about the Huck 8 scale. That's like the Mississippi River in Grand Rapids, versus the Marcel is really a different system. We're talking about less than a half of a square mile instead of, I think the average size of a Huck 8 in Minnesota is about, I don't know, between 1 and 2,000 square miles. So big difference. I'm sure a lot of folks are familiar, but I think it's worthwhile just to discuss kind of broad overview of how we do watershed planning and management in the state. We use what's called the watershed approach. It's a 10-year cycle where it starts with the pollution control agency with intensive watershed modeling, or excuse me, not modeling, monitoring. You move on to assessing the data, maybe building some HSPF models to help fill in some of the data gaps. You identify the impaired waters within that Huck 8 watershed. Again, this occurs at the Huck 8 scale. And then once impaired waters are identified, total maximum daily loads are developed for those watersheds, and watershed restoration and protection strategies, or RAPS documents, are created as well. Then it moves on to actual implementation. We move on to the Board of Water and Soil Resources that helps local governmental groups, soil water conservation districts, etc., come up with their one watershed, one plan, which helps to kind of chart a course, given what we know about the impairments in a watershed and some of these strategies for restoring and protecting what we already have. How do we go from that point to actual water quality improvement? After you have a few years of that actual implementation charted out within that one watershed, one plan, then you start back over at intensive watershed modeling. So it goes around in a 10-year cycle on the Huck 8 scale. So let's see. Excuse me, I got a comment. Sorry. What is a HUC? HUC is hydrologic unit code. It's the sort of national inventory of watersheds. Watershed being topographically defined area of land such that all water that drops onto the surface drains to a single point or a single cross section on the landscape. So HUC is hydrologic unit code. It means there's 8 digits within that, and it's a nested system where you have the HUC 8 being the big watershed comprised of many small watersheds as you kind of drill down to something like the Marcel. Many Marcels equals a HUC 8. Thank you for the question. I apologize for not defining my terminology off the bat. So how do forests fit in with this sort of 10-year watershed management and planning scenario? Thanks, Eli, for the HUC link. So as you can see in this map of impaired waters within the state, you can see a lot of them are in the western part of the state, a lot of them are in the southern part of the state. Well, we know that we have tile drained intensive cornfields, right? And an aspen harvest in northern Minnesota is going to be quite different. Not only is the landscape different, but just the whole management paradigm is different. So generally forestry is considered a low intensity land use as far as impacts to water quality, but you can have varying levels of intensity within silvicultural management that may bump it one direction or the other. So all of this kind of paradigm of water management in the state really has focused a lot on the agricultural areas. I'm used to speaking at the Minnesota Water Resource Conference, where I'm just about one of the only ones talking about what's going on in the forested area of the state, although we know that it's a huge portion of the state, and forestry is a large portion of the economy in the area and really a dominant land use in some of these areas of the state. So it's really critical to know how could this be affecting our waters and how do we plan for that to address some of those potential impairments or even know where we could possibly get impairments. So what do we know from small watersheds? That's the first thing. So a lot of the work, again, is done at the Marcel Experimental Forest. We're talking less than 1/2 of a square mile watershed size. We know that after aspen harvesting, water yield remains elevated for 15 years. Water yield being just the total amount of water flowing out as stream flow in a given year. Peak flow, or sort of our annual flood flow, can remain elevated from what we would expect had harvesting not occurred for about 7 to 15 plus years. And we can see actually very large increases in some of the channel forming and beyond stream flow discharge. You can see in this graph with the y-axis being the annual maximum stream flow and the x-axis being the return interval. Up to the 50-year plus return interval. So very low probability events, but very large magnitude events can increase due to some of this, due to harvesting in the years after. Keep in mind, this is at the Marcel, again, a small watershed. Further, we know that a partial cut is different than a clear cut. So when you have partial cutting, I imagine some folks have seen this chart before, where on the y-axis you have the change in your peak flow or your flood flow, and on the x-axis being the portion of the watershed in young forest or that had been harvested within the last 15 years. If only about 30% of the watershed area has been cut, generally we expect to see a decrease in the peak flow. This is because you have snowmelt desynchronization. All of the snow in the cut portion of the watershed melts first, and then you experience a small peak, and then the snowpack in the rest of the watershed melts, and you see a little bit larger of a peak, but now you have 2 peaks, one for the cut area and one for the forested area, but the actual size of any one peak is smaller than if it all pulsed out at once. However, once you harvest greater than about 60% of the watershed, then you're going to see very large increases in peak flows potentially. But so this is all great information and really excellent science that's been done at Marcel. But do the patterns of the importance of forest cover hold at the larger watershed spatial scale? Basically, the question being, is a large catchment or watershed just an aggregation of small watersheds, or are there other processes that emerge as dominant? There are several reasons to think why the Mississippi River at Grand Rapids or beyond could have different stream flow generating mechanisms than at the Marcel. to orient you to kind of this, there's a lot of arrows and stuff going on here, but I basically hashed out in green hash marks, basically the Marcel, a small headwater watershed with a bog in the middle. Then compare that to the large river cross section at the base of my sort of landscape unit here. Here you have a situation where the signal that's going to be in our stream flow, what's creating that stream flow, is going to have a lot more different pathways to make it to the river for that large river versus the Marcel. In the Marcel, you can maybe see a really large effect of harvesting because the water doesn't have to go through it doesn't have to jump through many hoops to come out as stream flow. Whereas at the large river, you see it maybe has to go through a fen, it maybe has to go through a lake. There are different kinds of wetlands, different forest types, and different ways that the rivers kind of merge together and things like that. Also, you have regional groundwater that might influence larger river flow, whereas at a smaller stream, you're going to mostly see maybe leakage to the regional aquifer instead of connection. In addition, you have maybe large-scale frontal movements coming in and driving the climate for a large watershed, that for a small watershed, you might just be like, oh, there's a storm, and there isn't as much of a large scale aspect to it. You're talking weather on a small watershed, you're talking more climate pattern at a large watershed. So this all leads us to finally the title of the talk, looking at the effect of the Pagami Creek fire on stream flow in the upper Kawishibwe River. So why are we looking at this? It's not a forest harvest. Fire will have probably a more severe effect on stream flow than a forest harvest, because in a fire, you'll have maybe hydrophobic soils or something like that from the ground getting scorched. It's much more of an intensive land change than maybe harvesting. But with
hey, Zach.
Yeah,
just a minute and a half.
Minute and a half. Oh, sure. Thank you. All right. So we're kind of looking at what's the most obvious place we would expect to see an effect. The upper Kawishibwe River is 650 square kilometers or 250 square miles. 30% of it is in storage, so lakes and wetlands, fractured crystalline bedrock, and it's almost entirely within the boundary waters. 30% of the area burned in the Pagami Creek fire. For my basic approach, I'll identify climatic drivers of stream flow and then analyze for the effects of the fire. I don't have much time left, but I want to point out that if you incorporate just precipitation instead of precipitation plus something else, you still have a trend here. So it's more than just precipitation that's driving stream flow in this area. There's another factor. We identified the Atlantic multi-decadal oscillation, which is a metric of average anomalies of sea surface temperatures in the North Atlantic that seem to be driving water yield and peak flows. After the fire, we noticed about a 30% increase in what we would have expected to see in water yield after the fire. You can see the y-axis is annual water yield, the x-axis is years after the fire, the black line is what we would have expected to see had the fire not occurred, and the dashed line being what we actually observed after the fire. But within 5 years, there was no effect of the fire on water yield. For peak flows, there's my alarm. There was no effect on peak flows. Basically, I apologize for going a little over here. It never goes as you practice it. But basically, what I want to point out is that there are other processes going on at these large watersheds that don't necessarily fall within the uncertainty envelope of what happens at the Marcel. We need to be cognizant of the scale at which we expect to see measurable results in this 10-year planning timeframe. And we might see different effects at large watersheds than what we would expect to see at small watersheds. Effects of harvest and land cover change are felt locally at the small scale versus on the more large scale. Thank you.